Good afternoon, everyone. We are the Great Brook Slope Stabilization Team. Our client is the town of Plainfield, Vermont, and George Springston. And our advisor for this project, whoever saw everything, was Adam Sevi, PhD, PE. And our team consisted of myself, Ryan McGuire, Vincent Wynn, and Mitchell O'Neill. So the quick agenda and overview of what our team will be discussing today is the main problem that our team faced, the scope of work, the methods we utilized to combat the risk assessment of the landslides, any lab work we had, hydrological studies that took place on the Great Brook, a slope analysis, a dam breach study, and an earned value analysis, as well as a final conclusion on everything that we assessed.
From research done by our client George Springston, Great Brook has been known to have several landslides, and the town of Plainfield experiences flooding from two old and undersized bridges. Our team has been tasked in assessing if the additional debris from the landslide will increase the amount of flooding Plainfield experiences. Our scope of work consists of finding soil parameters, the slope lithology, and doing a risk assessment, which includes finding total volume of failed material, a debris dam configuration, and potential dam buildup and flooding. First, we collected samples from all the layers present during our site visit. Then we classified them according to USGS. Next, we conducted a hydrological study to determine flow rates from various storms. From there, we developed a model using everything we found and collected to determine the slope stability. Using our data from our model, we then needed to determine if damming and breaching would occur, and if so, the resulting flow rate.
All soil samples were classified using the USGS classification method. All of the samples were found to be some combination of sand and silt. The angle of internal friction was also found, and they ranged from 39 degrees to 43. All of them were high, but not considered unbelievably high. The cohesion was found for only one layer of Great Brook 3 due to the only one layer being able to get a sample capable of having the cohesion run. We found the cohesion to be close to 10,000 psf, which is close to the area of a soft rock and not a silt or clay.
So one of the key significant aspects to this project that ties everything together is the hydrological study that was conducted on the Great Brook River. So in order to assess the hydro analysis of the Great Brook, a unihydrograph was made of the Great Brook River, and from that, peak flow rates from various yearly storms were assessed, and utilizing that information, we can compare the flow rates of storms to the landslide blockade, forming that water and then finally releasing it back into the Great Brook. And then also a convolution analysis of the Great Brook River was also conducted. So depicted from the slide is a unihydrograph, specifically the Q500 storm analysis for the Great Brook River. So essentially what a 500-year storm means, or Q500, is that the likelihood of this flow rate or storm happening any given year is 0.2% chance. And so this is significant because these storms usually have the most flow rate over a given certain amount of time. And so this is also important because you can take these unihydrographs and derive it into a convolution study that our group also did. And doing that, it gives you the total volume of water seen over the period of time the storm lasts, which is significant for not only the landslide, but the town of Plainfield, Vermont. So depicted on this slide is the total Great Brook hydro analysis. And essentially what all this data is a summary table for the flow rates of various types of storms that could be seen any given year for the Great Brook River. And so what our team did was we did a unihydrograph analysis for the 2-year peak all the way to the 500-year peak using lower bound intervals and upper bound intervals provided from the USGS. And doing this, we averaged them out and got it like a typical average peak flow of water you could see from any of these yearly storms. And so this is very vital and significant to our project because we can connect this back to if the landslide collapsed and formed a blockade of water building up, and then if that's released, we can calculate that flow rate and compare it back to one of these storms. And if it's similar to one of these storms, then we can realize that there could be a risk of flooding occurring from that landslide collapsing due to the knowledge we have given from the unihydrograph analysis.
Looking at the chart, the orange is no water table and the blue is with a water table. On average, there's a 78% decrease in the slope stability, and everything with a factor of safety above 1 is considered stable. And when there is a water table present, the slope was determined to be unstable for every single scenario. And each of the parameters are based off of a 15% change from the normal parameters as seen in the far left.
Now for the dam breach analysis, it was found that the maximum the dam could be while still blocking the entire stream was 5 feet tall. A dam of 5 feet tall was found to block a total of 1,089 cubic yards of water. Two methods were used to determine the flow rate when that dam failed. The first method, the FERC method using two equations, found the flow rate to be around 204 cubic feet per second. The other, using an NRCS program, found that flow rate to be around 179 cubic feet per second. Both of those flow rates are within the 1 to 2 year storm flow rates. This is our earned value analysis. Our estimated high cost was based off of 6 hours per week, with the low cost being 3 hours per week. As you can see, that we maintained pretty much closer to the high of our estimated. You can see a downtick between February and March due to spring break and the eventual COVID-19 relocation off campus. But by the end of the project, we ended up being over what we expected we would cost for this project. So in conclusion, we found that the slopes consisted mainly of low plasticity silts. We found that Great Brook 3 was found to be unstable during a 500-year storm event. A storm event of that size would cause around 1,500 cubic yards of material to fail and fall into the brook. The dam that would result from that material falling would impound around 1,089 cubic yards of water, which when fail would cause 200 cubic feet per second of flow rate added to the stream. Now, while these flow rates will not cause flooding in the town of Plainfield by themselves, it will cause additional flooding due to the fact that the town will experience flooding just based on the size of the storm itself.